Okay, hey guys, this is another video on B3 trig functions, and this is actually just covering the test. I thought I'd just go through questions on the test that you guys had last Friday, and if you haven't written it yet, then it'll still be a good review for the test you actually write. Okay, so basically trig functions in B3, we kind of just, our whole goal was mainly just to solve trig equations, but also we wanted to prove them, that the left side and the right side were equal. So this whole thing that you're seeing here are all the kind of identities and formulas that we know and are given to us on the test. So these cofunction identities, they say that the sine of pi over 2 minus x is equal to cos of x. So that's like saying, just to give you an idea of what that means, that's like saying the sine of pi over 2 minus, well, let's say it's pi over 2, is equal to cos of 2. So you can just sub any value in for x, and that's just letting you know that if we actually had the sine of pi over 2 minus pi over 2 is actually just 0, that's equal to the cosine of pi over 2. So we know that sine of 0 degrees, or radians, is equal to cos of 90 degrees, or radians, which makes sense, because if you looked at the curves, if you looked at the sine curve, it goes like this. So we all know it's sine, when sine is 0 radians, it has a y value of 0. So this is actually 0. And then cosine starts up here at 1. And then it goes like this. So then we know at 90, or pi over 2 radians, cosine has a value, a y value of 0. So right here at pi over 2 radians, the cos is 0. So we know that those two values are actually equal. So because the cosine graph or the sine graph is as if cosine was shifted 90 degrees, or pi over 2, they actually have the same value at those points. So cofunction identities just tell you when certain trig ratios are equal to the same thing. So you can use these, basically you can use all of these things to just sub things in and out of equations. And compound formulas are helpful because if we had something like sine pi over 3, we know we can use a special triangle to evaluate that. We know we can just grab our special triangle of pi over 3, and we know it would be equal to root 3 over 2. Cool. But if we actually had a combo like pi over 3 plus pi over 4, and we wanted to solve that, well, if we were to just add those values together, pi plus pi over 4, we would get 7 pi over 12. And I know that I don't have a special triangle for 7 pi over 12. And even if I did the terminal arm thing, 7 pi over 12 would be, I don't know, here. I know I don't have a special triangle for that value. So the reason that compound angle formulas are helpful is we can actually split sine pi over 3 up into sine pi over 3 cos pi over 4 plus cos pi over 3 sine pi over 4. So we can actually split so that we're able to use our special triangles to still solve it. And then the compound angle formulas also lead way to the double angle formulas. So, for example, if instead of sine a plus b, you had sine a plus a, so if you had this sine of pi over 3 plus pi over 3, so if these two values were actually the same inside, then we can use a double angle formula to help us solve stuff. Okay, and then these guys on the right-hand side, all of these ones, are ones from grade 11. So they're identical to the ones you learned last year, and you can just use them to prove trig identities. Okay, so so it's either going to say prove or solve, pretty much. Okay, so this guy says prove. So we want to show, basically, that the left side of this equation, the left side here, is equal to the right side. So I'm just going to try, I pick one side, I'm going to pick the left because it looks way more complicated. So I'll pick the left side. And I'm just going to try to sub stuff out. So cosecant pi over 2 minus x. If I look up here, I see cosecant pi over 2 minus x is actually equal to secant. Okie doke. So I'll just put it in, I'll put in secant x, see if that helps me. And then over, I know secant pi over 2 minus x is actually equal to cosecant. Okay, so I'll sub in a cosecant. So I basically just went to my cofunctions, identities, and I saw what cosecant was equal to, secant, and I just literally for that. That's all we're doing. And now I think I'm just going to use my reciprocal identities. So secant over cosecant. Well, I know secant is actually 1 over cos divided by, I know cosecant's actually 1 over sine x. I'm not loving the look of that. It looks ridiculous. So another way to write that, like I've got two fractions divided by each other. So this could also be written like cos x divided by 1 over sine x, if that looks any better to you. And I know, and I should know, this is seriously something you have to know. I can divide fractions by turning it to a multiplication and flipping the second fraction. And if you don't know that, like, start your skills, because things like that, it's such a hassle when you're trying to solve a hard problem and you can't do the easy part of the hard problem. So now I know 1 over cos times sine x over 1 will be equal to sine x over cos x. And I know from my quotient identity that sine x over cos x is actually just equal to tan x. So I've just proved it. So I know this is actually just tan x, which is, in fact, the right side. Boom. So now I know the left side is equal to the right side. And all it took was one minor substitution up here, and then just a bunch of fraction work, and that's it. So as you can see, I'm just heading up to my formulas and what the heck I can sub in. Okay, let's try another crazy one that I left myself no space to solve. So I see here that cos pi over 2 minus x equals 4 over 5. So I got this I know, and I know sine is equal to this. I also know that cos is adjacent over hypotenuse, and sine is opposite over adjacent. So I know a lot of people on their test jumped right to saying tan x would be 4, because opposite over adjacent is what tan is equal to. But I also know that cos pi over 2 minus x and sine pi over 2 minus x are equal to cos and sine, like they're the opposite guys here. So sine of pi over 2 minus x is actually cos x. So that's kind of crazy, but what I can do is I can actually replace this whole thing and say this is actually sine x is 4 over 5. What? And this guy right here, pi over 2 minus x thing, is actually cos x equals 3 over 5. So that's the crazy part. So what you thought was the opposite, oops, it's actually the adjacent side. What you thought was the adjacent is actually the opposite. So we know that tan x is actually equal to 4 over 3. Since this is an x. It'd be different if it said what's, tan of pi over 2 minus x equal to. But it doesn't say that. It wants to know what tan x is equal to. So we kind of want to change these guys so their arguments are in terms of x, which means we have to change sine pi over 2 minus x into a cos x. So kind of crazy, but again, all we did was use the cofunction identities. Okay, next step. These ones are really important. Solve in exact values. So these, here we go. We know as soon as it says exact, you can bet it's going to be our special triangles. So I would just like to write those out. So then I can just see what they are. So I know my two special triangles are these guys. Same as last year's, but now we're in radians. Okay, so now if I have 2 pi over 3, well, I'll try to use my terminal arm thing and see if I can solve it. So 2 pi over 3 would end up in this quadrant. So I know that angle is 2 pi over 3, and I know my related angle is pi over 3, which means I can totally use a special triangles to solve it. So there you go. So if I'm trying to find sine, I know I need opposite over hypotenuse. So root 3 over 2. Done. That was easy. I just had to draw it on the grid here and figure out my related angle and draw my special triangle, no problem. Okay, so next one, sine pi over 4 minus 3. That one looks crazy because I already know if I subtract these two angles, I'm going to end up with like pi over 12. And I know I don't have a special triangle for that. So luckily, pretty much as soon as I see this, to me, this looks exactly like sine A minus B. That's what it looks like. Instead of A, I've got an actual angle. So I'm going to head up to my compound angle formulas and look for the sine A minus B formula, which is right here. So I'm like just going to take that formula and use it. Okay, let's do it. So it goes and then a minus. Okay, cool. So it goes sine pi over 4 cos pi over 3 minus cos pi over 4 sine pi over 3. So I like actually just read it, which I better make sure that's right. So sine A minus B. Sine cos minus cosine. Let's see if I have that. Sine cos minus cosine. Yeah. And then I just use these two angles for A and B. Cool. Now this is pretty simple. Now I'm using these two special triangles and I'm looking at my pi over 4 angle here and I'm just reading off opposite is 1 and hypotenuse is root 2. So I know this is equal to 1 over root 2. And if you punched it on your calculator, like if you actually punched in sine of pi over 2, or if you're in degrees, sine of 45, it will spit out this answer, 1 over root 2, in decimal form probably. So your calculator can even do this for you. But we want exact values, so if your calculator can't do that, then use your unit circle, use your special triangles. Okay, cos of pi over 3. So now I'm just going to my triangle. Cos is adjacent over hypotenuse, so 1 over 2 minus cos of pi over 4, 1 over root 2, and sine of pi over 3, opposite over hypotenuse, so root 3 over 2. And that's it. The rest is just algebra skills. So now I'm just multiplying fractions. So 1 times 1 is 1, 2 times root 2 is 2 root 2. So 1 times root 3 is root 3, 2 times root 2 is 2 root 2. My denominators are the same, so I can subtract them. So I get 1 minus root 3 over 2. And you are welcome to leave it like that, except it's not completely right, because you should do something called rationalize the denominator. We don't love to have radicals in the denominator. So if we take that out, we'll just multiply the top and bottom by root 2. So my top will become root 2 times 1 minus root over. If I multiply the bottom of my fraction by root 2, let me write that in another color. So if I multiply this by root 2 times root 2, you can try it on your calculator if you don't know, but it would equal root 4, and root 4 is just 2. We already had another 2, so the bottom becomes. And in case you're not understanding that, let me show you over here. We've got 2 times root 2 times root 2. This becomes root 4. The square root of 4 is just 2. the whole thing becomes 4. That is just basic algebra skills. You need to be able to do that. And if you can't, calculator can be like a backup for you. All right. So this would be your final answer. Or if you felt like expanding the numerator, it would be root 2 minus root 6 over 4. Same thing. And that's your final answer. Okay, next one, we've got cos of pi over 12. So looking at that, I already know I don't have a special triangle for that. I don't know a pi over 12 special triangle. So it's making me think, well, what if I split this up into 2 separate values? So this is just playing around with numbers. So I know it's going to end up being this because I already subtracted those. So pi over 4 minus pi over 3. So I just try to use values that I know, like special triangles values, which are pi over 4, pi over 3, and pi over 6. So I just try to use a combo of those. So like if I put them all with a denominator of 12, that's 3 pi over 12, 4 pi over 12, and 2 pi over 12. And then all I'm doing is trying to make pi over 12. So I know if I subtract 4 pi over 12 minus 3 pi over 12, I know that's going to equal pi over 12. This is just a fraction game. So you're trying to create pi over 12 by adding or subtracting your triangles angles. And you're just playing around with it. And I know pi over 4 minus pi over 3. I'll just show you in case you don't know. Pi over 4 minus pi over 3. If I make them have the same denominator, multiply this guy by 3, multiply this guy by 4, I'll end up with 3 pi over 12. Ooh, I've done that wrong. Well, that's a good check for me. Minus 4 pi over 12, which would equal negative pi over 12. I don't want it to be negative though, so I gotta switch these guys around. Ooh, good thing I tried it. So it should actually go like that. That way I'll have 4 pi minus 3 pi, which would be positive 1. Cool, always good to check your work. Alrighty, so there we go. So I rewrote that as 2 things like that. And now I'm just going to consult my compound angle formulas for cosine A minus B. It will be cos A cos B plus sine A sine B. It's easy. So cos of pi over 3 cos pi over 4 plus sine pi over 3 sine pi over 4. And the whole entire point of this is just to get an exact answer instead of a decimal. Because we could totally punch this in our calculator, cos of pi over 12, and get an answer in like 2 seconds. But we want an exact answer, and we want to use our special triangles. So we find out cos pi over 3 is a half. I'm just using my special triangles at this point. Cos pi over 4 is 1 over root 2. Sine pi over 3, I think, is root 3 over 2. Yes, it is. And sine pi over 4 is 1 over root 2. This is going to work out like so similar to the last one. Root 3 to root 2. It's like pretty much the same, except it's a plus on top. So there's our answer, and then if we rationalize the denominator, we just multiply the top and bottom by root 2, leaving a 4 on the bottom. Cool. So that's it. Okay, and then this question on the test was rewrite in 1 trig ratio. This is like just recognizing, hey, you have a compound angle formula here. Compound angle formula. You just want to reverse. So you're looking for a sine A cos B minus cos A sine B. So we're looking for a sine cos minus. A sine minus looks like this guy right here. Sine A minus B is sine A cos B minus cos A sine B. Looks exactly like what we've got. And if it is, oh gosh, I already forgot. What was it? Sine A minus B? Pretty sure. Yeah. Okay, so it's a sine A minus B. Done, because that's A and that's B. That's it. Boom. 1 trig ratio. Did it. Okay, now we're moving on to trig identities. This is like the world's longest video. Okay, so we're trying to prove, we got here a left side and a right side, and we're trying to prove they're equal to each other. So again, you're just grabbing stuff from the top here, basically this side, but it could be any side, and you're subbing stuff in, and you're combining fractions, and you're doing whatever you can to make the sides equal to each other. So I'm going to start with my left side because it looks harder. And the first thing I think I'll do is sub tan x out for sine over cos. Because I notice I don't have any tans on my right side, so I might as well just get rid of it. Okay, so in doing that, right away I notice, because this would be like over 1, I notice that my cos cancel out, leaving me with a sine x, which I know is sine squared x. And using my Pythagorean identity, which is sine squared x plus cos squared x equals 1, that if I isolate sine squared x, and move that over, I get 1 minus cos squared x, which is exactly what I have on the right side. So I pretty much have just proved this, because that is equal to 1 minus cos squared x. So now I know my left side is equal to my right side. I'm like 2 steps. Okay, this one, sine squared plus cos squared plus tan squared equals 1 over cos. Okay. I don't know what to do. So I know that this plus this is equal to 1. So I could switch that out for a 1 plus tan squared x. I'm just working with my left side here. Why not? And then, since there's no tans on my right side, I'm going to do the classic switch tan to sine x, which will now have a squared in it. Totally getting somewhere, because now I have a cos squared on the bottom, which is what I have on the right side. So anytime I see two things, like a fraction and a whole number, I think to myself, why not make a common denominator? So I gotta multiply this fraction by cos squared x, top and bottom. Cos squared x over cos squared x plus sine squared x over cos squared x. And if I combine my fractions, I get cos squared x plus sine squared x over cos squared x. And I notice, this guy right here is your Pythagorean identity, which is just 1. Boom, proved it. Left side's equal to the right side. So all we did was we used a Pythagorean identity, used a reciprocal identity, made a common denominator, added them, used our Pythagorean identity, and we got it. Okay, and finally, the last part of the test was solving trig equations, and you had to solve it between an interval. Okay, so we've got tan 2x equals 1 over root 3. Okay, so right away I recognize these values as special triangles values. I know there's a 3, 2, 1 triangle, where this is pi over 3, and this is pi over 6. So right away I know that 2x, this angle, has to be, I'm thinking it has to be pi over 6, because then this would be my opposite side, and this would be my adjacent, and tan is opposite over adjacent. So if my angle was pi over 6, so if I had like tan of pi over 6, it would equal 1 over root 3. Right? Tan pi over 6 is opposite over adjacent, so that's right. And now I just want to find out what x equals, because I know like the whole angle is pi over 6. But if I wanted to just find x, then I'd have to isolate x, so I'd have to divide this by 2. Okay, sorry. Oops, I don't know what I was doing. Okay, so I have 2, so I'm dividing that by 2. Okay, so pi over 6 divided by 2, I know another way to say that is pi over 6 times a half, which means x must equal pi over 12 as my final answer. Okay, and then this one, 2 sine squared x minus sine x, looks It's like a quadratic. So you could just pick a letter like A, and we could just let A equal sine x for a minute. So this becomes 2a squared minus a minus 1. And now we want to factor this. So it's a complex trinomial. So I'm looking for two numbers that multiply to -2 and add to negative. So what would those numbers be? -2 plus 1, I believe. So I replace my middle term with the two numbers I find. So the two numbers are -2 and +1. And then I factor each half. So factor out 2a would be a minus 1. And I factor out pretty much nothing on this one, like a 1. So it becomes a minus 1 times 2a plus 1. There we go. So this was just a complex trinomial. And since I actually let a equal sine x, I eventually sub my sine x back in. 2 sine x plus 1. So there you go. So it actually equals that. And then if I just let each bracket equal 0 to solve, I get sine x equals 1. Sine x equals -1/2. And now I just have to solve those. So I personally know sine x is equal to 1. Here. And that's pretty much the only time before 2 pi. And I 90. So that's just like a value I know. It's one of like the special ones. So I know that x would equal pi over 2. Another way of knowing that is the unit circle. So knowing right here at 0, 1, I know that the x-coordinate is and the y-coordinate is sine. So I know at this point right here, sine x is 1, which is also at pi over 2. Or you can use your calculator to solve one like that. And it would give you 90 degrees, which is pi over 2. And then -1/2, looks like there's going to be a couple values here. And looks like they're going to be in quadrant 3 and 4. So I'm thinking special triangles wise, like it would be these two values. That would be the √3. So this angle must be pi over 6. So if I had to solve that, I would say we're looking for this principal angle. So this value here is pi. And then we have to add on a pi over 6. So we got a pi plus a pi over 6. We're at 6. So that would be 7 pi over 6. And we're going to have another value because it could also occur in quadrant 4. This would be pi over 6 because this would be -1 and 2. So I took 2 pi and subtracted pi over 6. I could get that angle. So if I just switch that over 6 and make that a 12, 11 pi over 6 as my two values. So I actually get 3 answers here. That's a lot. Cool. 1, 2, 3. Okay, also, I feel like I might have missed something here because it says between 0 and 2 pi, so I'm thinking, my bad, this was just one answer. There might be more. So it's positive, so if I look at my cast rule, I know it can only occur in quadrant 1 and 3, so I already found quadrant. Ooh, my battery's gonna die. Quadrant 1 was this guy, pi over 6. But then I think there should also be one over here. So this would be pi over 6. So to get there, I would do 7 pi over 6, I'm thinking. So that would be another angle that would work. So if tan 7 pi over 6 also equals 1 over root 3, then 7 pi over 6 must be a solution, but that's what equals 2x. So then I still have to divide that one by 2 to see what x equals, which would be 7 pi over 12. So we get 2 answers, and I almost missed one. Okay, those are tricky. Like if you don't have a good understanding already of what special triangles are and all, I think you will have a really hard time with this. But watch this video a few times, get some help. Good luck, guys.